Hey guys, Professor Doney back, and today we're talking about conservation of energy, conservation of E. The reason we talk about conservation of energy or talk about energy at all as a concept is because it is conserved and it is a scalar, so we don't have to worry about the sine cosine thing so much anymore. And it's just another way to solve some problems. So real quick on conservation of energy. Conservation energy says the energy total at point A equals the energy total at point B, or point 1 and point 2, or however we want to look at that. And the three energies that we've been looking at are potential due to gravity, potential due to a spring, and potential due to kinetic. So all those on one side have to be some combination on the other. Now it doesn't mean we have to have all those types of energy in every problem. It's just saying the combination of these three on the one side at one point has to equal the combination of those on the other. So if we do have a spring on this side and we don't on that side, we just include it where we have it. So let's do a quick problem here. Let's have a mass of 1 kilogram. It's a little over 2 pounds. And it's in a little ball, and what we're going to do is put that ball on a little platform that has a little spring, and we're going to load that spring kind of like a dart gun, and we're going to give that spring a spring stiffness or a constant of 100 Newton meters. Really what that tells us is what force it takes to compress it 1 meter. So it take 100 newtons or a little over 20 pounds to compress it a full meter. Not a very strong spring. Just putting some easy numbers here. And what we're going to do, that we'll call that point A, is we're going to release that, and it's obviously going to shoot the ball up. And eventually we expect the ball to reach the peak. And at the peak we know from earlier physics that the velocity in the y direction will go to 0. So we're looking at that situation, and we want to know how high up is that going to go. Now this is essentially a launch problem. We just don't know the initial velocity it's going to have. But what we do know is the spring down there, so we'll call that point A, we'll call that point B, and if we have time we'll come back here and find it at another point C. Alright, so how do we solve this? Well, we're using energy, so what we do is say all the energy we have at A has to go into all the energy we have at B. We don't have any non-conservative forces here, meaning friction. We're ignoring air resistance. There's nothing that's going to lose energy or leak energy. So what we have at the beginning has to be at top. Now what we do is basically go through this problem and say, all right, at point A, what do we have? Do we have spring? Do we have gravitational? Well, it's actually at h equals 0, so we don't. Do we have spring energy? Absolutely, there's a spring there. What about kinetic? Well, is it moving? No, so we have no kinetic. So on the A side, what we do is we have potential due to a spring. What do we have on the B side? Well, the B side, do we have gravitational? Absolutely, because it's at some height. Do we have a spring? No. Why? Because, well, no spring, as my students would yell out in class sometimes. Do we have kinetic energy? Well, we're going to say no, because our velocity goes to 0 at the peak. So on the left side, it's all potential due to gravity at point B. Now if we put in the equation for all of these, or each of these two, what we're going to have here is spring energy is half kx squared, and potential due to gravity is mgh. So I put half in there, the k is 100, compression, how far we compress it. Let's say 1 meter, I forgot to tell that, just for easy numbers, equals a 1 kilogram ball times 9.8 times h. If we go through that, it comes out to be 50 divided by 9.8, about 5.1 meters. Tells us how high up that's going to go. Now that's all based on energy. Energy doesn't care how it gets there. If it does this on the way up, or if it spins on the way up, it just says I have this much here, and I want to set that equal to what I have there, and that's how we solve those. So there's a quick energy problem. Understand if we drop this back from the 5.1, because the energy it has, it would compress the spring 1 meter. It's sort of that symmetry going on there. So hope you enjoyed that. Hope that worked out. And we will see you in the next video.